Okay, so today we'll do support vector machines in probably a fair amount of detail. So support vector machines you've probably all heard of are this. Okay, this is probably the easiest way of how to imagine what's going on. You have two sets and you want to keep them as far apart from each other as possible. And no, I didn't draw this, but if you do a Google image search on support vector machines, this comes up fairly early. And it's just, yeah, whatever. Okay, so let's go back to data points. So we have ham and spam, and remember we had a linear separator, and we could have many of those linear separators, right? And then, of course, the question is, which one's the best that you could possibly pick? And the best one that you could possibly pick is the black one because, as you would have already imagined, that's the guy that has the largest margin of separation from everything else. So let's just focus on this black guy. So what happens is, if you look, you can see that there are really only 3 points that matter in order to define this linear separator. So all those points here, right, I could just remove, and I would still get the same linear separation. And that's actually kind of nice, because it does two things. First of all, it makes my optimization problem a lot easier, because effectively, if I told you, those 3 points, those 3 support vectors, you could entirely obtain a solution. So that makes the optimization problem easier. Secondly, it also means that it's effectively a compression. And whenever you have a compression, then all sorts of nice information theoretic bounds kick in. And so if you're theoretically inclined, you can actually use this to define good uniform convergence bounds, as in if the training error is like this, then the test error has to be like that. And you can basically use the number of points that you need to define this hyperplane, so those 3. You can use that as a means of encoding the hyperplane and also therefore, getting very effective annotations. Okay, we will not do that in this class. This is something that fits squarely into statistical machine learning. So basically 10702 or 705. But this is a little bit too much math for 701. I want to have more time to actually focus on the algorithms rather than the theory here. And we've done a fair amount of theory. Any questions so far on the concept? Not on how to obtain it, but just on the concept of, why this is a good idea. Okay, I know it's Monday morning, really early. Let's see. So here's the math, right? So we basically go and find some linear function f of x is w of x plus b. And of course, what happens is that it has to be, greater or equal than 0 here. And it has to be less equal than 0. Less equal than -1 over there. Actually, here it needs to be negative, there it needs to be positive. And without loss of generality, I can set this boundary here to be 1 and -1 respectively. Right? And so when I do this, well, that's a large margin classifier. Okay. Now how do we find it? So one thing that you can do is you can focus on those 3 support vectors. And without loss of generality, the value for those points here has to be -1 and 1. Right? So we get w of x plus b equals 1. That's exactly what holds for this point here. And w of x plus b equals -1, which holds for these points over there. Right? And so now, what I can do is, I can just take the difference between those 2 terms, this one and that, and I have to get 2, right? So in other words, what I can do is I can take x plus minus x minus dot w. Okay, actually, let me do that explicitly in math, because it's a fairly important derivation. Okay. So remember we have w dot x plus, so that's basically a positive instance, plus b equals 1. And we have w dot x minus plus b equals minus 1. So that has to hold for some y equals 1 and y equals minus 1. Okay. Now if that's the case, then I can just take the difference between this. So this basically minus that entire expression here. And that, of course, gives me w dot x plus minus x minus equals 2. And so what I can do is I can just divide by the norm of w, right? And so what I get is that w divided by the norm of w dot x plus minus x minus equals 2 over the norm of w. But obviously we know that that this exactly measures the size of the margin. Right. So if you want to measure that size, right, that length, all you have to do is you have to take the inner product between the difference x plus minus x minus and the unit vector in the direction of that hyperplane. So that unit vector is nothing else than w divided by the norm of w. And so we're done. Okay. Now, therefore, if I want to maximize this margin here, I just need to minimize 1 over w. Okay? Yes?
So how do you find in practice the yellow points that are involved in the...
Very good question. So, okay. Okay, so let's, for the moment, assume I have some separating hyperplane. So basically I have some pair of w and b such that all the positives have, well, basically all the ones that have labeled yi equals 1 have positive value, and all the ones that are, have labeled minus 1 have negative value. Okay. So what you can always do is you can always scale up w and shift b in such a way that there will be 1 point touching things on either side, right? Now, how you find it overall, this is exactly the point of setting up a constrained optimization problem. So, because what you don't want to do is to actually manually, so to say, walk through all the points that are on the boundary and find things. That's exactly the thing you want to avoid, and this is exactly what constrained optimization will do. So, but the existence of such a pair has a lot to do with the fact that, well, if I can separate by a margin that is, greater than 0, then I can always shift and scale it in such a way that I hit things at values 1 and minus 1. Very good question. Thank you. Okay. Any other questions here? Okay. So now the point is we can turn this into an optimization problem. So the optimization problem, it's a constrained optimization problem. It's not a convex one yet. Is, okay, so the first good thing is already I have a linear constraint. I basically require that yi times x dot w plus b has to be greater or equal than 1. Okay. So in other words, we need to separate with a large margin. But now what I need to do is I need to find a w and b such that this margin is maximized. But this is not convex yet. But this actually can be fixed very easily. Namely, rather than maximizing 1 over the norm of W, I can minimize the norm of W, or minimize the norm of W squared. Minimizing the norm of W squared is a little bit easier in terms of optimization because you don't get all those inconvenient things around the origin. And yeah, so now you have a quadratic programming problem. So I hope everybody watched the video from last week, and you would have therefore seen what a quadratic programming problem looks like. Yeah. And this is exactly one of those. Okay, so the way to solve this is really just you plug this into your QP solver. So, for instance, there's something called CVX mod, CVX opt. So basically the CVX suite of solvers of basically Stephen Boyd and Vanderberger. Then there's something called OOQP. And there's, just do a Google search on quadratic programming solvers. I don't know whether the one from MATLAB by now is not horrible. Once upon a time, it used to be unusably horrible. It may be less horrible now. Okay. So in other words, if you use a new solver, you should probably check whether the solution quality is actually what you want. Okay. Any questions so far? Okay, good. So now we have this optimization problem, and it may not be the most amenable one, right? Because, we have all those complicated constraints. Can we make it a little bit simpler? Well, what we can do is we can just, go and write out the Lagrange function. So this is basically the same objective as what we had before. And now we introduce Lagrange multipliers, those alpha i's, that need to ensure that these constraints here are satisfied. Okay? And then, well, we just go and find the saddle point. So let's actually do that in practice. We went through this last week on the video on Thursday, where we looked at general quadratic programs. And now we're just looking at a special instance of such a general quadratic program. So there's nothing particularly complicated or fancy in it. It's just that we're going to go through this in detail. So the first thing that you want to do is you want to make sure that the derivatives in W and B vanish. So in other words, dWL and dBL have to be 0. Okay, that's the saddle point. Okay, so now if we do this, well, dW of L, well, 1/2 W squared just gives me W as the derivative. This is exactly why I picked the 1/2 in the beginning, such that I don't have to carry a factor of 2 around in my constraints afterwards. That's really just cosmetics, but it just makes the math look a little bit prettier. So in general, when you have an optimization problem with a quadratic term, or just, order p term, usually having something like 1 over p up front, will make the entire math afterwards look easier, and yeah, so it's a useful hint. Well, then we have the linear term. And now in the linear term, well, by linearity, the alphas and the y's and the xi's all go through. And all we have left is just the sum over alpha I, yi, xi. And this, of course, doesn't depend on x. So we get that first constraint. Let's actually rewrite this because it's really useful. What we get is that W equals sum over I, alpha I, yi, xi. Sorry, the font is still horrible. I tried a different stencil and it doesn't help. But basically what we get here is that W, so the solution vector, is given by a linear combination of the data points multiplied by their labels and then with some weight. Does somebody recall that type of expression from before? Okay? Exactly. So the perceptron has exactly the same properties, right? The key difference between the perceptron and this one here is that the instances can actually have weights. So they're going to have weights alpha I, and so far those weights can be anything from 0 to infinity. Well, not quite infinity, because that actually would mean that you would have a divergent dual, but yeah. So basically, the solution is very, very similar to what you get in a perceptron, with the main difference being that now you actually give the observations different weights depending on how important they are. Which actually measures quite well with the picture that we saw before, where we had this linear separator, right? And we only really cared about the support vectors here and nothing about the rest. Right? So this is exactly what happens, where you only really give those points on the boundary any non-trivial weights, and all those other points you can just throw them out. The other thing that you get is that the sum over alpha I yi equals 0. So if you ever did physics, this basically means that the forces pushing on either side have to be exactly matched. So those analogies aren't completely coincidental, because if you ever did theoretical mechanics, you would probably see that this is actually one of the first places where constrained optimization was introduced, where you have all the virtual forces and so on, and that's exactly the equivalent of this here. Okay. I don't know whether this is actually the context where constrained optimization was invented, but it's surely one of the first places where it occurred. Okay. Now, all we have to do is, since we just obtained the optimal solutions of B and W in terms of alpha, we can just plug them back into L. Okay. Who wants me to explicitly derive this equation, or who believes that by plugging W and B into L gives you this problem? Who wants to see the explicit derivation? Okay. It's probably about one-fifth of the audience, so okay, let's quickly go through this. And somebody's alarm clock is ringing. Maybe you could turn it off, please. Yeah. Okay. Okay, good. So, okay, let's zoom in a little bit. Okay, so if you recall, we had W equals sum over I going from 1 to M, alpha I, yi, xi. Now, this means that L can be written as, well, 1/2 norm of W squared minus, and so now I'm going to actually accumulate all those terms here in the first half of that sum, and I can realize that this is actually nothing else than W. So I get 1/2 W squared minus norm of W squared, and then I get plus, well, sum over alpha I yi times B. And this is, of course, going to vanish. And I get also plus sum over the alpha i's. Right? So that's really just plugging terms in directly. Okay. So with this term gone, and those two, of course, are going to be minus 1/2 W squared. I have as my objective L equals minus 1/2 W squared plus sum over I alpha I. And then I just plug in the expansion of the W's that I have here. And this gives me exactly the dual objective. Now, the only other thing that I have to do is I have to satisfy those two constraints, right? I have to satisfy this constraint and that one. Do I need to impose this constraint explicitly in the dual? No, I don't have to enforce it because the W's nowhere show up, and I've explicitly plugged that in when I use W. Okay. Now, do I have to enforce this the second constraint, right? Because I also plugged it in, so why would I care about it? Well, what happens is basically there is no explicit use of this constraint afterwards anymore, so I still need to satisfy it. This is in terms of the dual variables. Right? This one can be trivially satisfied, so I don't need to worry about it. This one is not trivially satisfied. Right? So I need to carry it around with me. That's what we have here. And then the last part, the alpha i's being greater or equal than 0, just has to do with the fact that these are Lagrange multipliers. And they're Lagrange multipliers for an inequality that I imposed. And since I had an inequality, I end up with another inequality afterwards. So this is a very useful sanity check. Free variables give me equalities. Inequalities give me inequalities. Equalities give me free variables. Right? Yep.
How do the two middle equations relate to the earlier Lagrange equations? Is it because W and B and alpha are not dependent upon each other that you get a 0?
No. W is still given by exactly that expression here, right? So basically what you do is you solve the problem, and then you read off the values of alpha. And that gives you the solution in W.
We found the saddle points by setting the derivatives to 0.
Correct.
The generic way, isn't it to write down the earlier Lagrange equations with partial derivatives?
Well, so what we did is we explicitly eliminated the primal variables from the Lagrange function. And in doing so, we end up with a quadratic program in the dual. So what you can do is, when you're trying to solve an optimization problem, you can do one of three different things. You can either try solving the primal optimization problem directly as it is. And sometimes that works, and quite often that's really painful. You can look for the saddle point in primal and dual. This is pretty much what the interior point solvers do. So if you recall from the lecture, from the video from last Wednesday, that's exactly what the interior point solvers do. They basically try to satisfy the primal constraints, the dual constraints, and the Kuhn-Tucker conditions, and therefore you're going for the saddle point directly. The third alternative is you go to the dual optimization problem, and now you have, in this case, a quadratic program again. And then you go and solve that quadratic program as you wish. So all we've done is we've just changed one quadratic program, namely the one above, well, actually on the previous slide, into another one that looks a little bit less menacing. Okay. And they are related to each other exactly by the fact that, well, this is the dual of the other one. Now you might ask, well, what about B? And it actually turns out that the dual variable to constrain this is what lets you read of B directly. That just has a lot to do with the fact that if you dualize yet again, you can recover primals. So in other words, if you have an interior point solver, then it will typically give you that dual variable as just an auxiliary result. And you can just read it off and plug it in, so you don't need to do anything else.
The problem with the dual thing again. So what do you mean by become? Like inequality become inequality? How
Okay.
exactly is this?
Oh, okay. So what happens is, let's take the simplest case of an unconstrained optimization problem, right? In an unconstrained optimization problem, I have some function f of x. Okay. And I want to minimize f of x with regard to x. So the first order conditions that we all know and love, and you guys should definitely know them already from before this class, is I set the derivative of f to be 0. Right? So I get f prime of x equals 0. That's an equality. And if I find an x that satisfies the condition that the derivative of f equals 0, well, that's basically now turning a minimization problem into a problem of solving an equation. Okay. Now, this is an example of where a free variable, namely x, an unconstrained one, becomes an equality in the dual. So the condition f prime of x equals 0 is exactly then the optimality condition in the dual, and it's just that since we don't have anything else there, that's all that there is to it. The objective function is essentially undefined. Or, it could be 0. Okay. Now, if I have a constraint, like this one here, right? So this is what we get from a constraint. I am going to invoke Lagrange multipliers, the alpha i's. So this was an inequality, and those alpha i's also on their own need to satisfy an inequality, namely alpha I greater or equal than 0, right? That's what we had here. So, in other words, this and that's exactly where one inequality leads to another inequality in the dual. And if I have an equality constraint, then I just need to get a Lagrange multiplier that's unconstrained. That's how those two things transform into each other. This is a really useful sanity check. If you compute the dual and that doesn't happen, it means you probably screwed up somewhere. Okay. Any other questions so far? Please watch that video. Okay. Now let's look at SVMs. Well, here's what we get, right? This is exactly the optimization problem, and here are our 3 points, the support vectors that are, always going to be support vectors. So now we can, of course, also ask the questions, when exactly do we have those alpha i's being non-zero? I mean, I already alluded to that when I said, well, this has to do with, points being exactly in the boundary. And that's exactly what's happening here, right? So remember, what you get as the optimality conditions is that Lagrange multiplier times constraint equals 0. Okay. That's this thing here. Now, that can only occur in 3 different cases. One case is out here, right? If I have a point like this here, it basically means that, the function here has to be greater than 0. So basically I have, obviously, yi xi dot w plus b greater than 0. Now that means that the corresponding alpha I, because I need to have that this equals 0, right? So this guy has to be 0. Likewise, for any point over here, I also get alpha I equals 0. The only time when those alpha i's may be non-zero is for those points exactly here on the boundary. So for those 3, I will actually get alpha I equals alpha I being allowed to be non-zero. And so now, since I know that these are exactly the points that give me the support vector expansion, so sum over alpha I, yi, xi, I know that w will be expanded only in terms of those 3 yellow points. Okay? Good. So, I mean, this is just a quick summary. We have a weighted linear combination of instances. Only the points really on the margin, on the boundary matter. Nothing else does. And I have a simple quadratic program. And on top of that, we can actually replace that inner product by a kernel. That insight that you can go from the standard inner product to a kernel took people about 30 years. Well, more like, no, 25 years. So the original optimization problem was published, I think, in 1968. And the nonlinear version was published in 1991 by the same author. So that very simple insight that I can replace xi.xi prime, xi.xj with k of xi and xj, that took Vapnik about 20 years, which is quite amazing, actually. Now, we're actually going to look at that in a bit more detail also in examples. Okay. Any questions so far? Yep.
So because the classifier disk basically depends on 2 points, doesn't this make the classifier very susceptible to noise?
You are spot on. This classifier right now is highly sensitive to noise. It's not very robust at all. So, for instance, if I was to draw another point here, well, let's draw another red point here. Okay, that wouldn't be too bad yet, because that red point would probably lead to that type of a separator, right? But if I was to draw a red point over here, then you couldn't even find a linear separator. So the current estimate is highly non-robust. And there are nice ways on how to fix this. And that took another 4 years from the 91 paper to the 95 paper. Okay. As a matter of fact, the idea was actually originally published 3 years before by basically Bennett and Mangasarian. And then Cortes and Vapnik picked that idea up 3 years later and forgot to cite it. Well, anyway, so here's an example of what happens. Some data. And, well, okay, so it's quite simple. I mean, there's basically a nice linear separator. And so one of the reasons why large margins are a good idea are because, well, if my data is slightly uncertain, then a large margin will make sure that if my data is slightly changed, I will still classify things correctly. Because if you recall, from the perceptron, you might have ended up picking, something that goes like so. Right? And in this case, of course, whenever that data point moves slightly, it might end up on the wrong side of the boundary. But, of course, I can entirely foul this up by just placing strategically 1 or 2 points very close to the boundary, even on the wrong side of the boundary, and then the problem isn't even solvable anymore. Okay. Quick question, what happens to our nice quadratic program if we throw some data at it where the problem isn't nicely solvable? Yep? It would not converge to a solution. Actually, worse than that, it's unbounded. So what happens is that the Primal problem is infeasible because there exists no W and B pair which satisfies all the constraints. And the dual will actually diverge. So this is another way of why going to the dual sometimes can be interesting, because it's a nice way of checking feasibility of a set of constraints. Any other questions? That's a good question. A good answer here. Sorry. Okay. So now let's get to the entire issue of soft margin classifiers. In other words, what happens if we have some points that are, poorly separated? So let's look at this, separator again. And if I have one point here now, then you can easily see, I don't need to prove this mathematically to you, that, well, this data isn't properly linearly separable, right? Because this one green point cannot be separated from the rest. Okay. And, okay, so now here's actually a rather unpleasant result by Minsky and Papert, which basically says that finding the minimum error separating hyperplane is NP-hard. Okay. So it looks like we're screwed, right? Because, well, we basically have that. And so finding the minimum error separator is impossible. And so, basically, how can we deal with that? Because, basically Minsky and Papert say, well, forget about solving that kind of problems. You can't really do it efficiently. And at the same time, we want to have a tractable optimization problem. And, well, the trick is essentially to change the question slightly. So this is, by the way, an extremely useful trick in many cases where you may have a problem that looks hard, possibly NP-hard, and then by just changing the question ever so slightly, you can actually solve it efficiently in polynomial time. And quite often that small change in the problem definition will not matter to the practitioner in the sense that which of those two definitions you pick, you can even argue which one of them is more desirable. However, some of them may actually give you rather nasty problems. So we had exactly that very situation for essentially novelty detection maybe about 10, 15 years ago. It was really funny. We were at a workshop. We presented our result on, well, basically novelty detection and so on, and having this polynomial time algorithm, and everything is well behaved and nice, and we got bounds, and the algorithm worked, and everything was beautiful. And the next speaker was Shai Ben David, who presented the result on the NP hardness of solving a problem that was very, very close to the one that we were solving. And so after those two talks, we looked at each other and was like, well, okay, so we can prove that we can solve it. And at the same time, well, there's the hardness result, so what gives? And once you looked at the very definitions, we found out that we were operating based on very slightly different assumptions. And that slight difference in assumptions made all the difference whether you can show that it's hopeless and give an explicit algorithm. So use that as a nice guiding principle, for your work, because quite often when you prove hardness, it's just that you made some assumptions that you can probably quite happily, get rid of and, still work with them. Okay, good. So the trick here in this case was to add slack variables. To realize that, well, okay, the minimum number of errors may not be exactly what I want. But, well, what if I could just relax the constraints slightly? And the way to relax them is to say, well, instead of, requiring that w of x plus b is less equal than -1, well, I'll just, add some slack to it, some psi. Likewise here. This is a common trick that you can do if you have constraints where you don't quite know whether they can be satisfied. You just add some slack variables to it, and then if I give somebody enough slack, they can still solve the problem, right? It's like saying, well, you need to, get the 100 points on the homework, well, which is probably kind of really hard. But if I tell you, well, you have to get 100 minus psi points, if you make psi sufficiently large, like 120, even a German Shepherd can solve it because you don't have to do anything, right? So this is exactly the trick where adding slack variables can turn a possibly unsolvable problem into something that's trivially solvable. So of course, since you're all way more intelligent than German Shepherds, we will of course not give you a psi equals 120, but maybe something smaller than that, right? So that's basically the same thing that we do here for the optimization problem. And so this is exactly where, that term here can be dealt with. And then all you want to do is just, minimize the amount of slack overall that you're getting. So this is really just summary from last Wednesday, if you didn't watch the video. Primal optimization problem is basically minimize f of x under the constraint ci of x less equal than 0. The Lagrange function is just, you add those constraints to it. First order optimality condition, well, you want the derivative to vanish. Then you go and solve for that primal variable, plug it back in, and you keep the explicit constraints. So use that as a cheat sheet in case you have optimization problems. Okay, so let's do that here. Remember, we had that convex optimization problem. And so there we go. Remember, the hard margin problem was just, 1/2 w squared under the constraint that everything is perfectly classified. So now what we do is we just say, well, this constraint has to hold, but with the additional slack. So that's what we basically added here. And of course, we want the slack to be greater or equal than 0. By the way, why do we want it to be greater or equal than 0? Yes?
Because the way you defined it was plus c on the negative and minus c on the positive.
Yes?
So it wouldn't be doing anything if it could be negative.
Well, if I want to minimize the sum over the slacks, right? Then having a negative psi might very well be okay, because essentially what this will let me do is it will let me, trade off accuracies in a way where I say, well, okay, I get this done extremely well, and so therefore I can screw up that other point even further, right? So you could do that. The problem is that classifying a particular instance extremely well to the detriment of something else isn't particularly effective. Because, that's like saying, well, I'm going to get, 11 points on some homework rather than 10, and so therefore I can, slack off somewhere else, which actually for the homework you can do, right? Because you can get bonus points. But we basically don't want to give our classifier bonus points. That's the equivalent of this, right? So now the problem is always feasible, because all I need to do is I set w and b equals 0, and I set the psi i's to be 1, and then of course, if I set w and b 0, then this term here will be 0, and then the psi i's being 1, it will just get 0 greater or equal than 1 minus 1, so that's trivially satisfied. So from that you can immediately see that the constraint optimization problem is always solvable in this case. Okay, so now we just plug in things again. So it's exactly the same optimization problem as before, just that now I have, another set of variables extra. Okay. So we have basically, you just look at the yellow pieces. So we have those psi i's. They come from the slacks. We now need to ensure that they are greater or equal than 0. So I have eta I psi I here. And that's what it is. So now we need to take derivatives with regard to w, b, and psi. And then we get a saddle point in alpha and eta. What we'll actually see is that we'll be able to get rid of the psi's and the etas entirely. And yeah, so basically those etas will just go away very, very painlessly. Is everybody okay with the optimization problem in the Lagrange function? Because it's really the same problem as what we had before, just with, some slacks added. There's conceptually no real difference here. It's just, cranking the handle and going through it. And by the way, you should crank that handle at some point for yourself. Yeah, probably after doing it 10, 15 times, you'll become proficient at it. There was a time when that would get you each time a new paper. Unfortunately, that time is gone, at least in machine learning. Okay. So let's look at the derivatives. And, well, the first one we already know, right? So the first one is just what we already have before anyway. Right? Basically, W equals sum over alpha yi xi. So that is entirely unchanged. The second term we also know, entirely unchanged. And mind you, this first term will effectively take care of this and that part. Right? So this will again, conspire to give us minus 1/2 norm of W squared. Okay. The second term will ensure that basically this thing here goes away. And so we are left with C minus alpha I minus eta I. So this expression here. By the way, why do I want to have a constant C in the entire problem here? So remember, C is basically the amount of penalty that I give the slack variables. What would a large value of C do? Okay.
Force the slacks to be very small.
Exactly. So a large value of C means I'm penalizing the slacks a lot, which means I'm going to get a solution that is very close to the hard constraint problem. If I make C very, very small, it'll encourage the solver to, maybe not respect the margins very much, and so I'll get a solution that is possibly has a lot of margin errors and possibly lots of errors. But it will also have a large margin, except that it's not a large margin for a lot of points anymore. Okay. So if I do this, well, just taking the derivative with regard to eta, with regard to the psi i's, I get this constraint. C minus alpha I minus eta I equals 0. So remember, the alpha i's are greater or equal than 0. The eta i's are greater or equal than 0. So what that really means is that the alpha i's are in the interval between 0 and C. And the eta i's are, of course, also greater or equal than 0. But that's basically, as long as the alpha i's are in that range, I can always satisfy the conditions on the etas. Right? Now, if you look at that, basically the derivative with regard to psi lets all the terms where psi was involved in go away. So that means this term here, and that term here. And so lo and behold, we get exactly the same type of optimization problem that we have before, namely the minus 1/2 W squared plus the sum of the alpha i's. That term here came from there, right? Because we had the alpha i's here and there. And we get the same equality constraint as what we had before, right? It's basically this term here. And then I get this additional condition that's written in green here. Okay. So now, this is actually kind of intuitive what's happening, right? This optimization problem here is always feasible, right? I can always pick some alphas that satisfy those constraints, like all the alphas being 0, in which case the objective here is 0. So that actually gives me an upper bound, so a lower bound on maximizing this, or a lower bound on minimizing the rest. And furthermore, it also means now that the influence of each individual point is constrained. Before that, in the support vector expansion, so basically in this expansion here, all the xi's could get a monstrous weight if that's what it took to actually keep data separated. Now, by constraining the weights of the alpha i's to be between 0 and C, I'm effectively constraining the relative weight relative to the total set of observations. So that actually makes the entire estimates a lot more robust. So it's different from the perceptron, where basically, whenever you make a mistake on that point, you keep on adding it. Here, at some point, you give up. Okay. Any questions so far? Okay. Well, then let's look at some examples of this. Okay, so the first thing, however, before we look at the examples, let's just go through the optimality conditions again. So remember before we had constraint times dual variable equals 0. And now here's what's happening, right? So we have, constraint times dual variable equals 0. And this as well. Okay, so when alpha equals 0, then, well, basically the constraints can do whatever they want. So these are basically all the points over here. Right? Whenever alpha is strictly in the interval between 0 and c, then this condition needs to hold, because we get exactly that thing here. Right? Okay, so you might ask, well, why couldn't actually any of the psi's be non-zero here? Well, because of this additional condition. And we know that alpha plus eta has to be, equals to c. And so basically this condition makes it impossible for both the psi's and the alphas to be switched on at the same time. So what that really means is that whenever I have a weight strictly between 0 and c, the point has to be exactly on the boundary. And then when alpha I equals c, so when basically the point is pushing as hard as it wants, it can essentially pierce that boundary and go wherever it wants. That's what we get. So basically, only those points for which alpha I equals c can actually become margin errors. So note that this is different from points being an error. Points being an error means that those points actually would be on the wrong side of the boundary. Here it simply means that they are on the wrong side of this margin. Okay. So let's actually look at that in pictures. So here's some data. And as you can immediately see that, well, not much happens as I increase c here. I'm basically going to get the large margin solution because finding everything solved perfectly just doesn't, that's just too easy, right? So it's amazingly boring. Changing c does nothing. Okay, so the data sets are very large, have a large margin of separation, and I can just perfectly separate them. Yep.
So in this example, if you have then impose the condition that each psi I is greater than 0, would it change the classifier as you increase the c?
Imposing psi I to be greater than 0, well, so a strict inequality is fairly awkward to deal with in constrained optimization problems. So strictly greater rather than greater or equal.
No. My question was if you didn't have that.
If you didn't have the size, you would get exactly the same solution here.
No, you didn't have the size.
Well, no. I mean, this is including the size. This is the soft margin solution. So what I'm going to show you now is that as you actually go and get different data that's noisier, because we're now going to go through the exactly same situation with, noisier data and noisier data yet, and we'll see how in those cases then different values of c actually affect the solution. So again, here you're not going to see very much yet, but what's already quite visible is, well, here are the support vectors, right? Okay. So these are support vectors. If I have c equals 2, nothing really changes. 5, 10, 15, 20, whatever. Nothing changes. Now let's pick data that's noisier yet. And what basically happens is, as you can already see, the size of the margin here gets smaller. So once the margin is small enough, or even it's not properly solvable otherwise, you will see that picking a different value of C will actually lead to a slightly different choice in margin. Let's see what happens here. I mean, we have 3 support vectors again. C equals 5. Nothing really happens yet. Okay, now let's see. Okay, so here's a data set where we can clearly not separate everything nicely with a large margin anymore, right? Because you would need something that goes like so. Okay, well, or something like that. And you can, if you squint hard or look at the handout as a PDF, you'll see that those points here are all support vectors. Okay, good. So now, as we increase things, you saw what happens. The margin actually gets a little bit smaller, and smaller still. And yeah, that's about it. So it's not a spectacular change. Once we go to nonlinear functions, we'll see a lot more changes. But since it's really hard to visualize nonlinear functions that are linear in some very high-dimensional feature space, I figured let's first start with the two-dimensional problems. So what basically happened is that the margin got smaller because I cared more about my slacks not being too large, but it didn't really change that much. Okay, so how do you solve this thing? Well, the first thing that you can do is you simply go and run the dual optimization problem. So that's how you get it. And if it's small enough, you can just use an off-the-shelf solver. So things like CVX-opt, Cplex, OQP, LoQuo, yeah, that's just fine. For larger problems, again, I mean, things like liblinear, for instance, would do a very good job. So there are a couple of existing support vector machine solvers out there that you can just use. So once upon a time, you pretty much had to code up your own. By now, yeah, you just use some existing solvers. And so, for instance, somebody like Chi-Chen Lin, he's probably spent the last 20 years trying, or maybe 15 years, trying to do a really good job at solving those problems. And his solver is pretty good. Every once in a while, probably every year or two, somebody comes up with, by the way, here's a way of how to make it much faster. But Chi-Chen just keeps on maintaining this code, so it's a good first default. Okay. So this was linear support vectors. What we're now going to do is we're going to go to the kernel trick, which you still remember from last week. And then we'll see how we can actually solve something like this. Okay. Any questions so far? Okay, good. So kernel trick is actually kind of easy, right? Because all we do is we just take all the places where inner products occurred, and we just do a query replace. Well, it's easy in hindsight once you know what you need to do. It wasn't easy when they wrote those papers. Basically, you need to deal with those places where the xi.w occurs, or xi.xj. So for the second and third case, it's trivial, because all you do is you just replace it by k of xi and xj. Right, same thing here. Okay, now there you need to actually plug in the kernel expansion. You need to plug in the expansion sum over alpha I, yi, xi that you had for the data points. Okay. And so you can just happily look at the optimization problem, and you don't really have to do much to, just read off the dual problem. As a matter of fact, your QP solver, unless you explicitly exploit it, won't really care whether you fed it the linear or the nonlinear optimization problem. Okay. So it's very, very simple once you know how to do it. Conceptually, it was non-trivial when they came up with it. Okay. Let's look at it in practice. So same type of data, c equals 1. And what you can already see here is something quite bizarre, right? You have support vectors at these 2 points, but this is also a support vector. Likewise here. So this happens because it's a linear separator in some high-dimensional high-dimensional space, and in that one, these may very well be boundary points. So the lines that I drew here are, this is where the function equals 0, here's where it equals 1, and here's where it equals -1. Those are the black lines. Okay, and if you compare between 1 and 2, nothing really changes, because it's all nicely linearly separable. Okay, now, for slightly noisier data, let's play the same game again. And you actually saw that something changed ever so slightly. And if you squint hard, you would have probably observed what was happening. This point here changed from being a margin error to no longer being a margin error, but being exactly on the boundary. Okay. Now, that's an example where the upper constraint was just barely touched. Yes?
What kind of kernel is it?
Oh, this was, I think, a Gaussian RBF kernel. Thanks for asking. Yeah. Now, as we keep on going, since my constraints are already satisfied, nothing happens. This is actually easy to see. If I solve an optimization problem where I have a constraint of the form 0 less equal than alpha I less equal than C, and that optimization problem is optimally solved for some alpha I being less than C, then changing C afterwards doesn't really change anything to the optimality anymore. Because all I'm doing is I just take a constraint set and I make it larger, right, and larger still. And so if the optimal solution was, say, here, then going from that set of constraints to the outer one, going from this set to the larger set, will not change optimality anymore, which is exactly what's happening here. Okay, so 50, 100, nothing happens. Okay, let's take noisier data, and now we will see things actually changing quite a bit. And you can see that now it basically doesn't have any errors anymore, not even margin errors, and that's why between 50 and 100 it doesn't change. Now you might argue whether this solution is actually better in terms of getting good estimates than this one here. And so basically what you'll already see is that choosing the right value of regularization matters. And once you get really noisy data, well, things start getting really messy as you increase the regularization. So, right. And what you can actually see, and that's pretty good, that even with this completely bizarre decision boundary, the actual decision boundary, which is this guy here, right, it doesn't really change very much from here to that, to that. Only once I go completely overboard on the regularization, as in I don't really regularize very much, will I get solutions that are probably quite horrible. Because I mean, if you look at that, that's how it's going to separate it. And then I have another decision, another boundary here and another one somewhere there, right? So something went horribly wrong. Yes?
How did you generate this data?
I picked two Gaussians with different amounts of noise. and then I just ran my SVM solver for different amounts of noise. So it's about as primitive as you want it.
So misclassification there is still a matter of noise, not a bad or the wrong model.
Well, in this okay, so wrong model. I mean, since I'm using kernels, you can actually, within reason, model pretty much any function that you'd want. So therefore, it's definitely not a matter of having a model that is not powerful enough. But what can happen? What happened here is that I just overfit like crazy. So given that I have another 10 minutes left, let's quickly look at what happens if I play with a different kernel. So this is basically just with a narrow kernel, I will get the same effects, but it just gets messier very quickly. With a wide kernel, okay, sorry, for some reason it doesn't display properly. Sorry, my keynote has serious problems right now. Sorry. Let me quickly quit out of this. Okay. Okay. Yep. So if you have a wide kernel, then even if you don't regularize very much, you still get a smooth outcome. So in other words, you actually have two parameters that interact in interesting ways of, how you can get a, nonlinear separation. You can either regularize very strongly, or you can pick a kernel function that is very wide, and so therefore it corresponds to very smooth functions. And both things will give you possibly good answers. And essentially, in one case, you don't pay much attention to the misclassified data points because your function class is just so inflexible that it cannot pay much attention to it. In the other case, you will simply disregard the penalty from classifying things very wrongly. And so therefore, even with a more sensitive function class, you're not going to pay much attention to things. So either of those two things will actually give you a good estimate. Now, which of the two you pick is very much a function of then, having good model selection. So what now happens is that unlike before in a lot of the homework where you had one parameter, now you're going to get two or more parameters to tune. And this is where it will then start becoming more interesting in terms of how you actually explore that function space. So probably you do not want to do a grid search anymore. Okay. So there's a couple of very nice tricks that you can use to adjust this, and we'll get to them later on. But basically one is, for instance, you want to get to a length scale that is comparable to the length scale in your data. So it's similar to Silverman's trick. Okay. So regression, we probably don't really have a lot of time to go through this, but I'll just quickly start with that. So basically, one thing that you could do is, and so let's take a step back, you could say, well, I just want to minimize my risk. Well, what do I care about all those constrained optimization problems, right? I could just say, well, I want to have some function f for which the risk, namely, for instance, the expected error of, whatever loss that I have, let's say, y is the true value of the stock, and f of x is what I predicted, that this discrepancy is minimized. And since I don't really know the full distribution, I could just go and approximate that by an empirical average. And then I could say, well, now I'm going to add a penalty to it, and let's solve the problem. As a matter of fact, that was basically programming homework number 2, right? So here's a simple thing that we can do, squared loss. Or I could have an L1 loss. So L1 loss basically means the absolute deviation between those two things matters. And so, for instance, on the stock market, you may, in some cases, care about absolute deviations. Or in some cases, if you have like an option that, where as long as you're within a certain range, you don't pay, otherwise you pay, you may very well have something like an epsilon insensitive loss. But basically, you may have a large class of different losses that you might want to pick. And so now what you can do is you can just go and write out an optimization problem. Okay, so the optimization problem is actually very simple. It's basically minimize yi minus, w.xi squared. And then I have, just the additional quadratic penalty. So this is exactly what we already did. Okay. And so now, this is an unconstrained optimization problem. I can go and just take its derivative. And so now, as its derivative, I will get a linear equation, which I can solve. Okay. So now if you look at this equation hard enough, you'll see that you basically have a matrix here, and then you have x times y. So again, you get the weighted linear combination of your data. Okay. So now that's a simple thing that you could do as just a simple, linear solver, and you get something that regresses linearly. But that's kind of boring. We want to do nonlinear things. So let's now go into Hilbert space. And in this context, I'm going to prove the representer theorem to you. This is also how the original proof went. It's very, very simple, but it's quite a powerful theorem. And after that, we'll probably need to stop anyway for today because the next lecture will come in. So let's say I want to, again, solve the optimization problem, minimize over W, just my regression as I would, and this penalty. But now this phi of xi is in possibly a very high dimensional space. So I cannot really ever read that off directly. But what I can do is I can just decompose W into something that lies in the span of the xi's and something that's orthogonal to it. So basically, these are all the xi's. Right? So they span this yellow space. And of course, if I do this and I plug it in here, I get W parallel plus W orthogonal. You can immediately see that you don't need the orthogonal part here. I can eliminate this. Because the orthogonal part will always equate to 0 if I take an inner product with phi of xi. Furthermore, I can see that the W squareds here, this also decomposes into W parallel plus W orthogonal. And since I want to minimize things, again, I can get rid of this. So therefore, what I get is that W optimal equals W parallel. And that is the representer theorem. This is one of the cooler papers in machine learning, and the proof is, just 3 lines. If you have more complicated functions than, the least mean squares and other things, it becomes maybe 5 lines or maybe 10 lines at the very worst, but it's a very straightforward argument. And now, the good thing is, if we know this, we can actually plug in directly what W should look like. So we can plug in this equation here directly into our optimization problem. And then you go and solve it. So you can directly solve for alpha. And you get this expression here. And this works amazingly well. So this gets you pretty much state-of-the-art nonlinear regressors. Now, how they work in a lot more detail, we will have to cover that on Wednesday. Okay, so thanks for your patience for today. I'll see you on Wednesday. Yes?
Is that the identity matrix or a vector of ones?
That's the vector of ones. Sorry, no, that's the identity matrix, yes. Yes. Yeah, it has to be because it's basically the norm of W squared that you get in.